Okay. Okay. So today's lecture will be devoted to conditional probabilities and Bayes theorem. And the initial topic was conditional probabilities and other paradoxes. But I try to insert some paradoxes or unusual considerations in every topic. That's why I've changed this particular one to include Bayes theorem rather than paradoxes in the name. So just a quick reminder that last time we introduced a precise definition of probabilities from the three Kolmogorov axioms. And those axioms are positivity, that the probability should be a positive function for any event. The second axiom is that probability of the whole space should be equal to 1, and it can be understood as the fact that something should always happen. And the third axiom is additivity axiom, which is written like that. So the probability of having two events happening at the same time, or at least one of the events happening, is equal to the sum of the probabilities of first event and the second event. And we also covered the fact that this has a hiccup, which is represented by this unusual union sign. And having it squared means that we need to have so-called mutually exclusive events, the ones that do not happen simultaneously, the ones that do not have an intersection or which have an empty space in the intersection. And in the general case, the sum rule also can be obtained. And then we just need to take away the probability of the intersection. And probability of the intersection can be dealt with using the product rule. And the product rule says that this probability of an intersection is equal to the product of the probabilities. But this is true only for independent events. And in fact, that's one of the possible definitions of independent events, that the probability of an intersection should be equal to the product of the probabilities. And another interesting fact that I would like to repeat is that independence is a very fragile thing. It can easily change with the change of a seemingly unrelated event. Do you remember an example where we demonstrated that? Well, if not, look at the slides again. So we consider it so-called Brownian rings, which were in our case represented by a binary machine that produced 4 different events. And if we removed just one of them, which seemingly was not connected to the other 3, then the whole independence notion for the remaining ones will change quite dramatically. And that is also very important because in real life, we are inclined to consider only the events or groups that are interesting to us. And we are inclined to assume independence as a given. But, well, as demonstrated in a simple example, it's not always the case. And real life examples, they just make things just a bit less visible, but we can have the same kind of processes. Okay, but let's move on. And let's move on from another simple but slightly not often covered problem. Well, and a simple question just to test that we all can use the chat. So that's a problem for you. Can you please, well, so usually I ask everybody to say hi in the chat to test the chat function. Can you please, instead of a hi, just write down the answer to this problem, please? So we flip a fair coin and we've got lots of heads, 2023. What is the probability to get a head again on the next flip? Yes, fair coin means 50% of getting heads and 50% getting tails. Yeah, great, absolutely. It's 50-50. Yeah, so who didn't test the chat function yet? It will participate. Very good. So indeed, the probability will be always 0.5 because this event doesn't depend on previous flips, as we assume. We have a fair coin. And it can be a bit confusing if we don't know this by heart, this property by heart, because it's easy to mix up it with probability to get that many heads in a row, which is indeed very, very, very low. But, well, we see if we had 2023 heads before, then probably it demonstrates that a coin is not as fair as we assumed, right? So the question is there a way to adjust our expectations from the evidence that we get? And we'll deal with it with several different ways. But now I would like to demonstrate a slightly different thing, slightly different approach. What to do if we don't know anything about a coin, about its fairness? Can we still get some meaningful information and use it without any knowledge at all? And it turns out that yes, it is possible to use even a biased or unknownly biased coin as a fair one, while actually with one important assumption that this coin has at least some different probabilities, that it's not totally strange one, not a totally cheat coin with just heads and just tails. That is that the probability of any of them is non-zero and non-one. For example, here as an example, I've chosen heads 0.4 and tails 0.6. And it is known as a so-called John von Neumann's method. And this method, to get a fair results, even from a biased coin, can be described in the following 3 steps. So instead of flipping the coin once, we flip the coin twice. And if we get 2 heads or 2 tails, we sort of discard everything and flip the coin twice again. But if we get head tails or tails head, then we just take an outcome of the first flip as sort of the fair coin. And it's quite a well-known algorithm to generate so-called bits of information, because obviously we can think that heads is say 0 and tails is say 1. So if we get head tails, then we say that we generate 0, and tails heads will generate 1. So why will it work? Well, let's look at the probabilities. So suppose that one of the probabilities is P, another probabilities is 1 minus P's Q, and the an important thing is to make them both non-zero and non-one. And because flips are independent, what is the probability of having 2 heads in this setting? Can you please answer in the chat? So what is the probability of having 2 heads if the probability of 1 head at 1 throw is P? Yeah, that's right. And if one of the, it's indeed the product of 2 independent probabilities, because it was mentioned that probabilities are independent. So thank you very much. It's indeed P multiplied by P or just P squared. Yeah, absolutely. And the same can be said about tails. It's Q squared. Now, what is the probability of getting head tails? Yeah, absolutely. The probability of having different results will be indeed the product of two probabilities, P multiplied by Q. And you see that that means that the events head tails and tails heads have the same probability, which means that we can consider them as one outcome of a fair coin. That's why it can be considered as a good information production or information generation machine. And we can see that in this way, if we have n biased bits, then we can produce NPQ unbiased outcomes. And it's a well-known method which can be considered, and there are multiple attempts to make it more efficient. And there is a link which goes to the paper who explains how to do just that. And you're welcome to follow it in your own time after the session. So everything is nice and cool, and we are able to generate fairness out of unfairness, right? Almost. But the main problem is in one of the important assumptions, which I think was coined by Vitaly in the chat. More precisely, the assumption that we have independent flips or independent events. In real life, probably if we are throwing a coin that many times, we are getting tired and so on and so on. And in other situations, usually the source of bias is not, or sources of bias are not independent. What should we do if we don't have independence at hand? And that's exactly what conditional probabilities is about. So conditional probabilities is defined like that. The probability that event A happened, if we assume that B happened, or on the condition that B happened, is defined as the probability of happening A and B at the same time, divided by the probability of B. And why is it a reasonable definition? Well, let's consider a simple example. So that's the Venn diagram with different probabilities. And suppose that the numbers or the probability values are working within each boundary. So, for example, how can we calculate the probability of event A? Event A consists of this unevenly shaped boundary, event B1 that is embedded inside A, and this event B2 that intersects A with the given probability. So, can you please answer in the chat, what is the probability of A? Yes, very good. So what is not 0.3 in the picture? It is the probability of getting into that uneven shape, sort of within the boundary. not getting into B1 or B2. So that's the probability of getting to A outside of B1 or B2. Yeah, very good. Yes, that's right. So we need just to add those probabilities, because then we are in the situation of mutually exclusive events with probability 0.1, 0.3, 0.12. Now, conditional probabilities. What is the probability of having A if we are in the situation B1? Yeah, very good, absolutely. Then the probability of probability of having A if we are in situation B1 is indeed 1. And similarly, we can find that the probability of A if we are in situation B2 consists of B2 consists of 2 parts, and then this probability of having A if you are in situation B2, it will be equal to the probability of getting in the intersection divided by the probability into getting the full B2. And similarly for B3, because B3 is outside, then this probability means that we will never get into A. That's the probability equal to 0. So that's just a quick illustration of how the conditional probabilities work. Now let's consider a more practical example of how can we use the freshly defined definition. We have a well-known in the population color blindness problem, and we know that color blindness is unevenly distributed between male and female. That is, that men are 60 times more likely to have it than female. Suppose in a population we have equal male to female ratio. And suppose we know that about 4% of all people are colorblind. And we would like to know what will be the probability of having a colorblind person if you look at a certain male, at a random male. And what is the probability of having a colorblind person if we are considering female? So let's solve this problem. The probability of having a colorblind male is probability of male multiplied by the probability of having colorblind person, which is this, which is approximately 2%. Okay? And similarly for female, we can multiply the numbers in a similar way. And probability of female will be again 0.5, because we assume that we have an even distribution of male and female in a population, multiplied by the probability to be colorblind, and we get the same. Isn't it strange? Because we know that males are 60 times more likely to be colorblind. So where's the catch? The catch is that the product rule applies only to, to independent events. Because from the conditional probabilities, we can have general product rule that for any events A and B, not necessarily independent, we will have the product of the probability of intersection in B is equal to the probability of A conditioned on B multiplied by the probability B. And it trivially follows from the definition of conditional probability. How about independent events? Well, we can easily check that for the independent events, that will be the same as we had before, and the probability of having C conditioned on D will indeed be equal to the probability of C using our definition of independent events, which conforms to our common sense understanding of independence. So now we can sort of match two definitions of independence, the one that we gave last time, and the new one that for independent events, the probability of having one event if another happens is the same as when we do not consider the second event. And it's a symmetric property. Right. So also quite a useful thing is so-called law of total probability. And that's quite a trivial, another follow-up from the definition of conditional probabilities with combination of the third axiom. So what will happen if we separate the whole space into disjoint, non-intersecting, multiple exclusive events, then we can just represent the probability of the total event A as a sum, relevant sum of conditional probabilities of A conditioned on any of those events multiplied by the probability of those events. It's quite a trivial property, but it's very useful. So let's use it on our problem of color blindness. And let us remind again the problem here. So men are 16 times more likely to have color blindness than female, and female-male population ratio is 50-50, and we think that about 4% of all people are colorblind. So let's use whatever we gained now, all the definitions, to find the conditional probabilities. So we know that the total probability by the law of total events can be separated into two cases of having colorblind male and colorblind female, which we can rewrite using conditional probabilities. And then, since we know that probabilities of male and female are the same, then we can take out of the brackets this probability of being male or female. And then using the property that color blindness in male is 16 times more probable than in female, then we can represent this as a final equation. So 4% is equal to 0.5 multiplied by 17 multiplied by this conditional probability. From here, we can compute this conditional probability is equal to approximately 0.5%. And since colorblind male is 16 times higher, then we can get that one as well. And that's again quite a real life situation, because that's what we quite often can measure. We can measure the prevalence of a disease in the whole population. We know that risk factor for one part of the population is larger than for another part of the population, and from there we can find a similar conditional probabilities of testing for disease, like color blindness in this case. That's quite a useful possibility in itself, and it can be improved even further by addition of another quite obvious but quite useful theorem, which is called Bayes formula or Bayes theorem, whilst in fact it should be really historically known as Bayes-Price-Laplace formula, because Bayes sort of formulated this theorem, but he didn't propagate this knowledge any further. And it was Price and Laplace who made this theorem well defined and well known to the world as it is now. So this theorem is written in front of us, and it gives us just another tool to quickly calculate this conditional probability of A conditioned on B through the known probability of B conditioned on A, and via the probabilities of events A and event B. And well, here's a proof from the definitions, and here's also a diagram which visually illustrates this quite simple and quite natural fact. Well, let's try ourselves on applying this theorem. So suppose we forgot everything that we've just learned, and suppose we have a new problem. We know conditional probability of having a disease for a male. We know the probability of disease for a female, and we know the prevalence of this disease condition for the population. And we found that a certain person indeed does have this disease, in this case, color blindness. And the question is, what is the probability that this person is, say, a male? And to get the result, we just use the base formula. We write it down, then use numbers and get the result. And similarly, we can find the conditional probability that the randomly taken person was a female with color blindness, with the disease was female, by using a similar formula. And well, you see, previously we sort of knew that the prevalence for male was 16 times higher, and we've got the same result here from different initial input, which means that, well, the results match each other, and we are doing basically everything right. That's quite a reasonable answer in itself, isn't it? Well, it's all very trivial, isn't it? But it's so useful and so non-trivial in certain settings that there are still publications quite recently. So, for example, this publication, in fact, just rewrites or explains this theorem to clinicians. And this publication was from 2010. And a similar publication, again, quite a recent one, 2011, again explains Bayes' theorem. Why? It's so obvious. Well, to see that, let's deal with another unavoidable, very well-known problem, so-called Monty Hall puzzle. And Monty Hall problem appeared from an American show with the name Let's Make a Deal, which was very popular, I think, in the middle of the 20th century, well, after the World War, I think in the 60s. It was hosted by Monty Hall. And actually, in the 90s, when the Soviet Union collapsed, this exactly show was also transferred into the whole area of newly discovered former Soviet republics. And we also had this very game just a bit later in the 90s. And it was a very popular thing indeed. Why? Well, let's have a look. It looks trivial, but is it? So what is the show? In the show, the host had 3 doors, and participants knew that that a prize is behind one of the doors, and behind the other 2 doors there was a goat. Well, it was in the initial Monty Hall game. In Russian version, there was something much less valuable than a goat, so no winning there. And the contestant chooses one of the doors, but it's not opened yet. Before the door is opened, Monty Hall reveals another door, which always has a code. And then he asks, do you want to switch doors or stick to your original choice? What will you answer? Can you please answer in the chat? What is your choice? Would you stick to your choice or will you switch? Just one word. Is it stick or switch? Yeah, we're all very clever people here. All those equally likely? It's an interesting question. So for participants, all those are the same unless they have a certain method, but we don't know about that. So participant can indeed choose any of the doors with, oh, well, for participant, it doesn't matter to start with. But then host always opens the door with a code. So he will never open the two remaining doors equally likely. The host will never open a door with a car. So there is still some, well, obviously there should be some trick left, some choice behind. So how to justify the answer? Let's use Bayes' theorem. So suppose we denote Ci, the fact that the door is behind, the fact that the car is hiding behind the door I, say C1, the fact that the car is hiding behind the door 1. And Xi, let's denote it the player's choice of the relevant door. And Gi, well, the similar fact of having a goat behind the relevant door. And initially, answering to Vitaly's question, we assume that the probability of having a car behind any of the door is the same. So the doors are indeed equally likely in that sense. That is one of the three. Now consider the situation if the player chooses one of the doors. Doesn't matter which one, for example, door 1. And suppose the host opens the door number 3. Then consider the possible scenarios. The conditional probability of having the car behind the third door in this particular situation, if we have already got there, is obviously equal to 0. Well, let's deal with the remaining similar conditional probabilities. So the probability of having car under the second door, if we sort of reserve the first door, and if there is a goat under the third door, can be represented using the Bayes theorem like that. And because we already know, as we've just, that probability of having the goat under the third door is equal to 1, we sort of inserted, or Monty Hall inserted the certainty. We can further evaluate the probabilities, write them down like that, and get that the probability of having the car under the second door is 2/3. What does it mean? Well, that means that indeed it will be better to switch to the second door than to stay with a choice of the first door, because then the probability of having the car under the first door will be 1 minus 2/3, that is 1/3. And for many people, it was pretty much counterintuitive. And I remember how many people did not want to switch to another door in a similar game. Well, especially if they were considered some different variations of this game. And it was quite a big thing there. In a picture, it's possible to consider all different scenarios and see in more visual way, if you are still not sort of convinced by the formulas, that indeed that's the best strategy. The best strategy is to switch. But why the formulas are so useful? Well, because they automate the process. And that's where the Bayesian networks stem from. So Bayesian networks, they allow to automatically update our previous knowledge from the newly obtained knowledge. So from the knowledge that the door number 3 does not contain a car, we're able to update our knowledge about whereabouts of the car now. And in a similar way, in Bayesian networks, we are able to adjust our knowledge. So that's a very useful automated thing and a very popular one. And I will touch on that yet again when talking about hypothesis testing. Because in fact, it gives the whole birth to another whole area or branch of probability theory, which is called Bayesian probability. But for now, let's stick to practical examples, and let's consider another practical question: how Bayesian theory, how Bayes' theorem could be used to help in real-life scenarios. So suppose we know that at the age of 40, about 1% of women have breast cancer. And we know that some kind of screening gives true positive result for 80% and gives false positive result for 10%. And we have one woman who tested positive. What's the probability of cancer for her? So that's everything that we have in our problem, rewritten in mathematical terms of conditional probabilities, and our task is to find the probability of having cancer if we are getting positive result. Why is it so why is it so, why is it a valid question? Well, because the knee-jerk reaction and the first attempt at the answer is to say that, well, we know that the test is 80% accurate. And surely it means that if we found a positive result, then it should be 80% accurate. So the first knee-jerk answer to that conditional question is 80%. Well, let's check it. Let's redo it using the Bayes theorem. So using the Bayes theorem, we can rewrite this probability. Well, that's the Bayes theorem in front of you. So we can rewrite the probability we are interested in, the probability of having cancer with a positive result as this. Now, denominator is quite often a most complicated part, but luckily we have enough information here to find it from the law of total probabilities. So in our situation, it will be approximately 10%. Then the conditional probability that we need, probability of having cancer in a positive result, is 0.8 multiplied by 1% divided by 10%, which is approximately 7%. That's quite different from 80%, isn't it? And this is totally not intuitive for most of the people. Just recently, I was talking to a friend who was given a positive result in a Down syndrome for a baby situation. And that is a very real life case. And very similarly, we know that Down syndrome has quite similar division of probabilities, and accuracy of the test was also similar to this particular case. And she was, well, very, very worried, understandably. So why is the probability so small? It turns out that this posterior probability is so small because the cancer-free or disease-free group is huge compared to the disease group, which means that false positives will have a huge effect on any kind of even a good test. And it's known as a base rate fallacy. We sort of often assume that the conditional probabilities are symmetric, but they are not. So the probability of having cancer in a positive test is not the same as the probability of having a positive test if somebody has cancer. And to see that, it's quite useful to try playing with different numbers in there on such a simple case as this, because then we can sort of visualize and test, try our hands on what exactly is going on. So suppose we change the sort of accuracy or positivity of the test. Suppose the probability of having a positive or catching cancer is slightly lower. What will change to the how the interesting probability of having cancer with a positive result will change? Well, it will be lower. That's quite obvious. But the question is how much lower? And it turns out that not so much. So we've changed that input by 10%, and the output will change just by 1%. Okay, let's improve our test and suppose it catches every possible case of cancer, which means that the probability of having a positive test in cancer is 100%. That's as ideal as it could be, right? It turns out that the probability of having cancer, if somebody tested positive, is just 9%. So quite a low number still, not 100%, not even near. Now, how about the impact of false positives? So let's set back the probability of having a positive result in cancer to 80% as before. But let's change the probability of being positive for no cancer to 20%. That is, increase it by 10%, similar to what we did with the first conditional probability. Well, it turns out that the probability of having cancer, the probability that interests us, is 4% now. So again, 10% change in the input will lead to about 3% change of the output. Right. But I've mentioned something about the rarity of the disease. So let's have a look at that. What if we change the rarity of the disease and take the probability of having cancer to 2%? What will happen then? It turns out that with all other input being the same as before, the probability will change to 14%. So just 1% change in this type of the input will give us quite a substantial change in the output in percentages. So in fact, the impact of the disease rate in the population is the, well, most noticeable usually. And that's why it's so important to test not everybody. Well, no test is absolutely accurate. There are still some false positives and false negatives, which means that even if somebody will be tested positive, then quite often it's just an unnecessary worry if the disease is rare. And that's why we need to balance the rareness of the disease with the possibilities of devastating consequences from it. Well, and coming back to the mentioned case of the Down syndrome, that's why the most sort of impact or the probabilities are a bit higher for people where the disease rate is thought to be a bit higher, that is for women that are a bit older. But I just wonder if it will change in the future as well. And just finalize with that worrying story. My friend, she has given birth and everything is perfectly fine with the baby. So, well, we've covered the sort of the famous, well, paradox or fallacy, which is called base rate fallacy. And also quite often some kind of other rates are used as well, but they do not improve the situation because similar smallness sort of rule will work in this case. So old-fashioned conditional probabilities are just easier to update and work following mathematical rules. So measuring accuracy is not as easy a task as we might think. And that's a question for you. Suppose we know, as before, that about 1% of women have breast cancer. Can we suggest a simplest possible way to create a test that will be 99% accurate? Yeah, brilliant question, Gabriela. Thank you very much. Because accuracy is very misleading. And quite often in machine learning, accuracy is measured as just simple coincidence with the true results, with the ground truth. So if we measure accuracy in this way, then returning a negative result always will coincide with the ground truth in 99% of cases. And then it's so easy to claim that our tool is 99% accurate. And well, it's a sort of a joke, but in every joke there is a part from the joke. As far as I know, there was one of the COVID testing centers, which was during COVID, sort of under investigation for essentially doing a very, very similar thing. So it still happens. And that's why accuracy should indeed be measured in a slightly more clever way. And that is done by introducing true positives and false positives, true negatives and false negatives, which we all heard about, and they are called sensitivity and specificity. So sensitivity measures how true are our positives, and specificity measures how specific we are for this disease, or the number of correct rejections of negative results. So, and I particularly like this picture, which is introduced by Wikipedia, of how we measure it. And I think we all seen it many, many times during, well, sometimes even television programs during recent COVID, didn't we? But there's also other ways to measure accuracy. Specifically, in machine learning, we are often dealing with precision and recall. And that's a very similar thing indeed. So you see the picture is the same. Yeah. The definitions are ever so slightly different. So can you, if you have a good memory, or if you have a good notion of what is sensitivity and specificity, can you see which one of sensitivity and specificity is mentioned here by another name? So we have recall, which is defined like, well, relevant retrieved divided by all relevant, or all positives. and we have precision, which is defined as true positives divided by all predictions. Yeah. So how is it compared to specificity and sensitivity from the previous slide? Any ideas? Okay, I'll demonstrate them side by side. So is it easier to see now? Which of those two notions are different? Which one coincides? So what are the coinciding definitions or items? Yeah, I think just from the picture, I'm quite a visual person, so I prefer pictures. We can see that sensitivity is the same thing as recall. Yeah. And that's quite a useful thing to be able to translate one thing from another, because machine learning tools, they often stem from classical statistical tools. And knowing how one is translated to another, how one is connected to another, can really help. Well, similarly, after we define this way of measuring accuracy, we can try to do many other kind of measurements. And quite often, it's all represented in so-called contingency table, where, well, there's one of the examples from Wikipedia, in fact, for a concrete example with some numbers. But let's have a look what we have. We have what we had before: true positives, false positives, false negatives, true negatives, and in fact, sensitivity, specificity, and things like that, they will follow by comparing those four main numbers. That's indeed sensitivity here, but also there is possible to define many other measurements for or between all of them. Similarly, in machine learning, we know that as confusion matrix, and it looks indeed very similar, with again the main four in here, and even sensitivity recall in there, yeah, and all other parameters also mentioned. But if you compare the two slides, there are also some different items in there. Well, noticeably, in machine learning, there are new things like markedness, Folks-Mallows index, Matthews correlation coefficient, which did not appear before. So why is it happening? And why is it happening? I will try to explain by looking at one of the scores that is in fact present on both tables. It's called as an F-score. That's one of the scores that is very often used in real-life evaluations. So F-score is defined as a harmonic mean of precision and recall. Why is it useful? Well, because we have precision, we have recall, but it's so nice to have just one measurement tool, just one number to deal with, isn't it? It's easier to make graphs, and easier, especially for automatic recognition and automatic decision, to have just one number instead of dealing with two dimensions, which are slightly, well, less obviously interconnected. So that's what F-score is about. So that's a definition. And actually, we know that we would like to balance precision and recall. And it is possible to balance them by generalizing the F-score. So we add some importance weight to the measurement. And all very nice and well. But the main problem is that F-score, no matter how we define it, will depend very much on the ratio of positive to negative cases. So what does it mean? It means that we have large problems for imbalanced classes. And that's a very real life situation. because, well, in general life, why did we measure precision instead of specificity? That happens because the number of true negatives in real life is usually not known. We do not measure absolutely everything. And we assume that the number of true negatives is huge. And in fact, sometimes it's truly unknown, or sometimes it's just assumed to trump everything else, to trump all positive cases. Which means, as we've just discovered, quite a lot of problems in using the F-score. And that is why there are multiple different other attempts to sort of make a more symmetric type of measurement, in particular this Matthews correlation coefficient, because correlation coefficient will behave more symmetrically to the classes. Well, also not ideal. That's why other attempts are there. But in fact, they do not work 100%, but they can be suitable only for certain tasks. And there is an easy way to connect them all using mathematics, precision recall, using mathematics and Bayes' formula. So we can just revert precision as this conditional probability and recall as sort of opposite conditional probability. And then we can also define a so-called well-known thing as no-skill classifier or dummy classifier. And that is the thing that we always want to have, something that implements the most simple possible formulas without any conditions at all. That is the one that assumes that classification is not dependent on the class, sort of dummy or ideal case. But then we can calculate that precision will be, in fact, constant and will be equal to class frequency. And recall will also be constant and be just a probability for positive classification. And that is, in fact, the case that we've discovered or suggested when having a large but not very meaningful accuracy. Right, that's basically all I wanted to say about the conditional probabilities and their use. And just a homework question for you. One of the possibilities to modify Monte Hall problem in a slightly different setting. But you see, I really like changing small things dynamically and see how the result will change as a result. So try that. And there's a brief summary of what we've covered. Next, we've defined the conditional probability and checked that their independence is still understandable in the way we did before. To deal with conditions, we can use Bayesian theorem. And we also learned that accuracy is not an obvious thing, and sensitivity, specificity, precision, and recall, they are essential inputs, and it's hard to replace them blindly by a single measurement, no matter how many attempts are made. Well, and in fact, this analysis becomes even more challenging if we have some missing elements or missing cases, and that I hope will be the topic of the next lecture next week by Gabriela. Are there any questions?
Thank you, Olga. Great. Gabriela, since you are present here, maybe you could introduce your lecture yourself for the next week very briefly. Gabriela, you're
muted. Okay, so next week I will be talking about a problem of missing data. So when you are doing a data science or artificial intelligence project, you have a data set that was collected previously, And there may be some values that are missing for various reasons, such as, for example, somebody forgot to write down the number, or maybe patient couldn't sustain a particular test and therefore that particular measurement hasn't been done. So what do we actually do in these cases? Do we need to worry? And what are the strategies about it? I will be using the conditional probability a lot because I will be asking about the mechanisms of missingness, and I will be showing some examples. That's all. And if I can say one more thing, I found one book extremely useful for my understanding of probability, and I wish I found it much sooner. And that's a book by Gerd Gigerenzer, Reckoning with Risk. So he mentions Monty Hall problem and also all other things, including screening programs and how they've been wrongly done. And also another very important book by Judah Pearl called The Book of Why, where he talks even more about paradoxes and also Monty Hall problem. Yeah.
Yeah, thank you very much, Gabriel. It's very helpful. Yeah.
Yes, I have just Googled this book, Reckoning with Risk, from 2003, right?
Can you possibly share the link in the chat so that
Yes.
once you found it, and I'll stop recording.
Yes, I have a link